Hello, good morning, students. Are you able to listen me? You can reply with a message also. Okay. So actually, our syllabus is over. We have completed all the 5 modules, but still we have 8 more days for your semester to end because your last working day is 23rd of January. So what we will do in these 8 days is, if you have any doubt or any problem, if you are facing in any topic, you can tell me. I will repeat it once again. Till that time, what we can do is we can concentrate on the important questions. That is what you can say 10 marks questions in all the modules. We will just have a recap. Okay. From the first module, we will start today. If you have any doubt regarding anything, you can ask me. Okay. So in the first module, we have 10 marks questions, different 10 marks questions. In that, what we can do is we can just have a recap of that. So I am sharing the screen. You tell me whether it is visible to you or not. So is the screen visible to you? There is some internet connectivity problem. I am trying to rejoin once again. Okay. Okay. So in the first module, the most expected question for 10 marks is with respect to your capillarity. That is capillary rise and capillary fall. So that we will see today. 2 marks questions, 5 marks questions you can do it easily, but for 10 marks question, what we can do is once again we will repeat it because we have time also. So this is capillarity, right? So what is capillarity? Capillarity is defined as the phenomena of rise or fall of liquid surface in a small tube relative to the adjacent general level of liquid when the tube is held vertically in the liquid. So what we are trying to say, we have taken a beaker in which we have filled the water or any other liquid suppose. After that what we are doing, we are inserting a glass tube in it, and the way in which we are inserting is we are inserting it vertically inside the beaker. So what will happen, because both of its ends are open, the upper end is exposed to atmosphere whereas the bottom end is exposed to water. So some amount of liquid will enter from this tube into the glass tube. So this is the initial level of the water in the glass in the beaker. But after when you have inserted the glass tube, there is a rise in the level of liquid by an amount h. So this h is known as your capillary rise. So what we are saying, the rise of liquid surface is known as capillary rise. Or if suppose there may be a fall in the level of liquid also. If suppose when you insert the glass tube into the beaker, what will happen, the amount of water entering the glass tube may reduce also, and you may get a condition for capillary fall. See here in this way. So what is happening here, this is the initial amount of water, but the amount of water which is filled in the glass tube is lesser than the level of water in the beaker. So this is known as capillary fall. So you need to understand what do you mean by capillarity. Next you need to understand what do you mean by capillary rise, and finally you have to understand what do you mean by capillary fall. So what is capillarity? Capillarity is defined as the phenomena of rise or fall of a liquid surface in a small tube relative to the adjacent general level of liquid when the tube is held vertically in the liquid. So don't get confused. The three terms are different. Capillarity is different, capillary rise is different, capillary fall is different. Normally, capillary rise is nothing but rise in the level of liquid surface. when a glass tube is inserted in a beaker containing water. Similarly, capillary fall is nothing but fall in the level of liquid surface. But when you say capillarity, it may be either rise or fall because it is a phenomena. Capillarity is the phenomena of rise or fall in the level of liquid surface when a glass tube is held vertically in a beaker and both of its ends are open. Okay, I hope it is clear to you. Now coming to the derivation of expression for capillary rise. In exam, you may get either capillary rise derivation or capillary fall. Or in the most unlikeliest case, you may get a problem on this. Okay, so what is the expression for capillary rise? How you will find out? What we are doing is consider a glass tube of small diameter d. What we are doing is we are assuming the diameter of this glass tube as what happened. See, mute yourself, Mubashir, or else it will be a disturbance for others also. So what is the expression for capillary rise? What we are doing, consider a glass tube of small diameter d which is open at both ends and is inserted in a liquid, say water. So what we are trying to do, we are trying to consider a glass tube of small diameter d. So this is your glass tube whose diameter is small d and it is inserted in a liquid, say water. The liquid will rise in the tube above the level of liquid. So what is happening here? There is a case of rise in the level of liquid. So that's why we are calling it as capillary rise. Let a small h be the height of the liquid in the tube. So what we are doing, small h, we are calling it as height of liquid in the tube. Or in other words, this is nothing but your capillary rise. Small h is nothing but capillary rise. Now, under a state of equilibrium, the weight of liquid of height h is balanced by the force at the surface of the liquid in the tube. See here in most of the cases for fluid mechanics or any other subject you take such as physics and all, we consider the equilibrium condition or we resolve the conditions for example you say summation of horizontal force is equal to 0, summation of vertical forces is equal to 0, or summation of moments is equal to 0. In your strength of materials you might have also done. So normally to derive an equation, what you can say, in order to derive a equation, what we have to do is, one second, okay. In order to derive an equation, we generally consider the equilibrium condition, or what you can say, conditions which are there to in order to get the final answer. So here what we are doing, we are considering the condition of equilibrium. Equilibrium is a condition in which the summation of horizontal, what you can say, uh, forces acting on a fluid is zero. So here what we are trying to say, under the state of equilibrium, the weight of liquid of height h. See here, this liquid is there, it may have some weight. Yes, say whatever it may be, it will have some weight, some kgs you say. So this weight of the liquid is balanced by the force of the liquid in the tube due to surface tension. So once again, we have to come across surface tensions. What is surface tension? Surface tension is nothing but tensile force acting on the surface of a liquid, or tensile force acting between two immiscible liquid is your surface tension. So this weight of the fluid in the glass tube is balanced by the surface tensile force. So now we have to calculate the weight of the fluid element as well as surface tensile force. let sigma equal to surface tension of liquid. What we are doing, we are assuming that this sigma is equal to surface tension of the liquid. Similarly, theta is equal to angle of contact between liquid and glass tube. Theta is nothing but your angle of contact between this liquid and glass tube. This glass tube is empty earlier, but when you apply or when you insert water into it, there will be a contact between the water molecule as well as the glass molecule. So that angle we are calling it as theta. Now weight of liquid of height h in the tube is given by area of tube into this height into rho into g. So this formula you have to remember to calculate the weight of liquid. So how we are calculating weight of liquid? Area of tube, area of this glass tube into height, this h into density. This liquid will have some density into g. Now area of this glass tube is calculated using the formula pi by 4 into d square. Area of this glass tube, because it is a circular tube, area of the tube is given by pi by 4 d square. Next into h into rho into g, where rho is the density of the liquid. Now equation 1 you see, instead of calling this as equation 1.17, we can call this as equation 1. That is equation for weight of liquid of height in h in the tube is known to you. Now one more force you have to calculate, that is surface tensile force. It is vertical component of surface tensile force. See, whenever a force is there, there will be horizontal component and vertical component. So this surface tensile force is acting on the surface. So we are interested in the vertical component. Vertical component of the surface tensile force is given by sigma, which is nothing but your surface tension, into circumference into cos theta. So how you will calculate circumference? If you see the figure, this is a circular glass tube. So this circumference is nothing but pi into diameter d, that is circumference of a circle. So your equation changes to sigma into circumference. In place of circumference, you can write pi into d cos theta. Now you call this as equation 2. Instead of calling this as 1.18, call this as equation 2. Now for equilibrium, what we have to do? We have to equate equation 1 and 2. Once again, you try to understand why we are equating equation 1 and 2. As I said you, for our analysis, in most of the cases, what we assume, summation of forces acting in upward direction is equal to summation of forces acting in downward direction. Similarly, summation of forces acting in right hand side is equal to summation of forces acting on the left hand side. Or in other case, what we do, summation of forces acting in clockwise direction is equal to summation of forces acting in downward direction. So all these are called as your equilibrium condition. So if you see the figure, what is happening here is this glass tube is filled with liquid. So there will be some weight of the fluid element. 1 second. I have to take up a call. हेलो वालेकुम बोलो हाँ वालेकुम सलाम okay. Now what we have to do is, we have see here, if you see the glass tube, what is happening here is surface tensile force is acting at the top on this portion, whereas this force, what you can say, weight of the fluid element is acting in this direction. So surface tensile force is acting in upward direction, weight of the fluid element is acting in downward direction. So you have to resolve these two forces. That's why what we are doing, that is first portion, that is weight of the fluid element in downward direction, pi by 4 d square into h into rho into g. This is equal to sigma into pi d cos theta. sigma into pi d cos theta. Now what we are trying to do, this h is equal to sigma pi d cos theta divided by this portion we are taking to the denominator. Both these terms, if we calculate, your h comes out to be 4 sigma cos theta divided by rho j d. Now the value of theta between water and clean glass tube is approximately equal to 0. Hence cos 0 is equal to unity. See here what we are trying to say. This is the standard equation for capillary rise, that is small h is equal to 4 sigma cos theta divided by rho j d. This is your final equation. But for water particularly, the value of theta between water and clean glass tube is approximately equal to 0. This theta is becoming as 0. Now cos 0 is equal to 1. So this entire portion changes to small h is equal to 4 sigma divided by rho g d. So this is the final equation for capillary rise. So in exam, you may get a question in this way: define capillarity and derive an expression for capillary rise. Or you can get a question in this way also: define capillary rise, prove that h is equal to 4 sigma divided by rho g d. In both the cases, you have to write the same answer. I hope it is clear to you. If not, you tell me, I will repeat it once again. Or else we can move to capillary form. Yes, you can reply with a message. Have you understood the derivation? Or you want me to repeat? Okay, okay. See, from equation 1 and 2, you want me to explain once again. You see here, what is our equation 1? Our equation 1 is nothing but weight of the fluid element. This is equal to pi by 4, that is area of the glass tube, into d square, into h is your height, capillary rise, into rho is your density, g is acceleration due to gravity. This is equal to sigma. What it is equation to? It is nothing but vertical component of surface tensile force, or what you can say, force due to surface tension. This is equal to sigma pi d cos theta. Now we are interested in calculating h, that is capillary rise. So this h will be equal to sigma pi d cos theta as it is. This pi by 4 d square into rho into g, if you take from this side, it will come to the denominator here. Now if you see, this 4 goes to the numerator. This pi d gets cancelled. So what will remain? 4 sigma cos theta in the numerator divided by this pi d is cancelled, 1 d will remain, rho into g. So your h is equal to nothing but your capillary rise, which is equal to 4 sigma cos theta divided by rho into g into d. This is your final equation for capillary rise. I hope it is clear to you now. Okay, now we will go to capillary form. So if the glass tube is dipped in mercury, the level of mercury in the tube will be lower than the general level of the outside liquid as shown in the figure. See here, you can remember in this way also. Whenever we derive the equation for capillary rise, our liquid will be water, whose density is 1000 kg per meter cube. But when we derive any equation for capillary fall, the liquid will be a heavy liquid whose density is more. For example, in most of the cases, your liquid will be mercury, whose density is 13,600 kg per meter cube. Okay. So as the density of mercury is more, what is happening? The mercury which is there inside this beaker, it is in filling the glass tube, but to a small extent only. It is not filling up to the extent to which the it is filled in the beaker. Whereas in capillary rise, what is happening? The water was crossing this level and it was going to up to this mark. This is the difference between capillary rise and capillary fall. So if the glass tube is dipped in mercury, the level of mercury in the tube will be lower than the general level of the outside liquid as shown in the figure. So if you can see the figure, it is clearly here what is happening when you have inserted the glass tube in mercury. Because the density of mercury is more, it is not filling entirely inside this glass tube. It is filling up to only this point. So this we are calling it as capillary fall or capillary depression. Let small h is equal to height of depression in the tube. This small h we are calling it as height of depression in the tube. Now what we are doing, then in equilibrium, two forces acting on the mercury inside the tube. Now also two forces will act on the fluid element, but the kind of forces is different. One force is same, that is first one is due to surface tensile force acting in downward direction, and it is equal to sigma pi d cos theta. Same was the case in capillary rise. Here also surface tensile force will be there, sigma, which will be equal to sigma pi d cos theta. But the change is, there we have taken weight of the fluid element, but here what we have to take, second force is due to hydrostatic force acting upward, and it is equal to intensity of pressure at a depth h into area. See here, this is the change. If you see the figure also, here also you can easily notice the difference between capillary rise and capillary fall. There also two forces were there. I will just go back to capillary rise. Here also two forces are there. One is due to surface tensile force acting in downward direction. Another is weight of the fluid element in the glass tube. If you see the capillary fall derivation or diagram, here also surface tensile force is there. But instead of weight of fluid element, because there is no fluid element inside the glass tube, so instead of weight of fluid element, what we are taking, hydrostatic force acting in upward direction. Now comes the question, what do you mean by hydrostatic force? Generally hydrostatic force is a kind of force which is exerted or which is produced by the liquid which is present inside any container or beaker. So this you can also observe in case of rivers, oceans and seas. When the tides or floods will come, what will happen? The water which is settled calmly inside the rivers, oceans, what it will do? It will suddenly burst out. This is due to hydrostatic force. Or one more example for hydrostatic force you can see is your fishes, sharks, what they will do? They will come up at the top of the surface of the water. Why it is so? Because the hydrostatic force which is there inside the water, it will push them to the upside. So hydrostatic force is nothing but a kind of force which is produced by the flowing water, as a result of which the water molecules rises to the upside. So here also what is happening, second force is due to hydrostatic force and is acting in upward direction, and it is equal to intensity of pressure at a depth h. So this is the depth into area. Now what will be your equation? Intensity of pressure. We are interested in hydrostatic force. Force generally is nothing but pressure into area. Pressure into area. Area of what you can say circular portion is pi by 4 d square. Now if you see, pressure is nothing but rho g h. How you calculate pressure? Density into acceleration due to gravity into height of the fluid element. So in place of P, what you can write? Rho G H into pi by 4 d square. Now we have to equate the two equations. That is, your first equation is due to surface tensile force, that is sigma pi d cos theta. This is equal to rho G H into pi by 4 d square. If you calculate H, we are interested in calculating H. So this 4 goes to this side. 4 sigma cos theta divided by rho GD. So pi d here, again it will get cancelled. Now, if you see this equation with the capillary rise equation, both the equations are same. Here also we got 4 sigma cos theta by rho GD. Here also we have got 4 sigma cos theta divided by rho GD. But the difference is with respect to angle theta. That is angle of contact made by the glass tube with the liquid present. There the angle of contact was 0 degree. So cos 0 was 1. So H becomes 4 sigma by rho GD. But here if you see, in case of capillary fall, the value of theta for mercury and glass tube is 128 degree. So if you take the value of theta as 128 degree, it will be negative. So if you have calculators, you can try enter your home also. So the answer you will get, it will be in negative. So this indicates there is a fall in the level of liquid surface. So this is the equation for capillary fall. I hope it is clear to you. If not, you tell me, I will repeat it once again. You will get a 10 marks definite question either on capillary rise or capillary fall, whichever may be the university, either VTU, KVNU, whatever it may be, you may get a question for capillary rise definitely. So tell me if you have any doubts. Do you want me to repeat it once again? Have any doubt, you can ask me. Or else we can move to the problems. No doubts? Have you understood capillary rise as well as capillary fall derivations? Okay, we will solve one problem. It will be easy for you because you may get either a derivation or a problem on this topic. So calculate the capillary rise in a glass tube of 2.5 mm dia when immersed vertically in water in first case and in mercury in the second case. Take surface tension as sigma is equal to 0.0725 Newton per meter for water and sigma is equal to 0.52 Newton per meter for mercury in contact with air. The specific gravity for mercury is given as 13.6 and angle of contact is given as 130 degree. So what you have to calculate is capillary rise you have to calculate. Diameter is given as 2.5 mm. First, what we are doing, we are inserting the glass tube in water. In the first case, we are inserting the glass tube in water, whereas in the second case, we are inserting the glass tube in mercury. So the surface tension of the fluid is also given to as sigma is equal to 0.0725 Newton per meter. For water, it is this much, and for what you can say mercury, it is sigma is equal to 0.52 Newton per meter for mercury. Now, the specific gravity for mercury is 13.6 and angle of contact is 130 degree. So what we will do, we will write down the things which are given to you. That is diameter of tube is 2.5 mm, or if you convert this will be 2.5 into 10 raised to minus 3 meter. Next, surface tension for water is 0.0725 Newton per meter. Similarly, for mercury, the surface tension will be 0.52 Newton per meter. It is given, whereas specific gravity is 13.6. And density, if specific gravity is known to you, we can easily calculate the density of any fluid. How? By multiplying with 1000. Now, in the first case, what is happening is you need to calculate the capillary rise for water. That is theta equal to 0 degree. That is H is equal to 4 sigma cos 0 divided by rho g d. Now, here they have not mentioned cos theta because for capillary rise for water theta equal to 0, cos 0 again it comes out to be 1 only. You can write it or you can leave it. Okay, 4 into sigma is given to as 0.0725, the rho is 1000, g is 9.81, this you have to remember, d is 2.5 into 10 raised to minus 3. If you do the calculation, it comes out to be 0.0118 meter, or if you convert this to centimeter, it will be 1.18 centimeter. Similarly, for mercury, the angle of contact between mercury and glass tube is theta equal to 130 degree. It is given. So your H is equal to 4 sigma cos theta divided by rho GD. 4 into sigma is 0.52. Cos in place of 30 theta you can write 130. Rho G, density of what you can say mercury is 13.6 into 1000 into 9.81. Diameter is same 2.5 to 10 raised to minus 3. So if you do the calculation, H comes out to be minus 0.04 meter. So this negative sign indicates that there is a capillary fall or depression. I hope it is clear to you. If not, if you have any doubt, you can. So from the first module, you may get one or two 10 marks question. So the likely 10 mark questions are capillary rise, capillary fall, and problem on it. Okay. Either of the three, you will get two. Or in some cases, you may get one also. Do you have any doubt? No doubts? So VTU students, you can start writing the BMT lab file also, and you can submit it, okay, once you have completed. So we will conclude now.